Hello, everyone. I'm Billy Younger, and I just finished solving how to design a banked curve so that you don't need friction. I made a video on that. Now I'm going to take the actual result and show you how to actually put it in your calculator and get a feasible amount or a feasible angle for the banking. In this case, I'm going to assume that you're leaving the off ramp. I know often it's an exit ramp that has like a 25-mile-per-hour speed limit. In this case, I'm going to figure something that's closer to 30 because that's the way most people drive. I've also found various documents suggesting these things might be 1,700 feet in radius, which is a really huge radius. They can make them a lot smaller, of course. Uh, and that would, of course, cause the banking to be much higher. But in this case, from what I've read, this should be on the order of 2 to 3% grade. So we'll get it, and that's going to turn out to be close to 2 degrees. But we'll work it out and show you how to do it. So let's begin. So right here, you see this is the problem that I solved in the other video, and you see that my final result was theta equals the inverse tangent of v squared over gr. We found that the masses actually canceled out right here. That's why this answer doesn't have a mass in it, and that means it's good for all vehicles, no matter what their mass. And this was again without friction. So what I said was we're going to do this for 30 miles per hour because that's a fairly reasonable speed that someone's probably going to go. I'm going to use 1,640 feet, which is about 500 meters. And 30 miles per hour turns out to be about 48 kilometers per hour. And really, in our system, we need the units to be in meters per second. So that's about 13.3 meters per second. If you're having difficulties converting units, then by all means, look at one of my videos on how to convert units. So now all I got to do is plug all this into the inverse tangent formula. And I'm going to say theta is equal to the tangent inverse of v squared. So that'd be 13.3 meters per second squared over g, which is 9.80 meters per second squared, times r, which is 500 meters. So I think you can tell what's going to happen with the units here. This top one, since the square is going to become meters squared per second squared. So this will cancel out both this one right here, since the whole thing squared is going to cancel out this meter and this second. Since the whole thing squared is going to cancel out both of these second squared. So we end up getting a dimensionless quantity inside the tangent, but that's how it should be. Tangent is opposite over adjacent, but that generally means is two sides lengths divided by each other, so they should actually have no units. So when we actually do this, we get that it's the inverse tangent of, plugging this all into my calculator, I got 0.0361 roughly. Now, remember, you got to make sure your calculator is in degree mode if you expect this answer to spit out a degree. But if you want it in radians, you're going to have to have it in radian mode for it to spit out a radian. When I do this calculation, it turns out to be 2.067. I was using 3 sig figs, which in reality I should have been using 2 sig figs. So really, this is degrees, but I'm going to say it should really be called about 2.1 degrees. Now, I looked up a couple of publications, and all of them are quite old, but one of them was from the University of Texas, and they suggested that you, if you're moving at 48 kilometers per hour, actually they used 50 kilometers per hour, and you go around a 500-meter banked curve, that banked curve should be between 0.2 and 0.3% grade. 0.2 and 0.3% grade means 2 units of height for every 100 unit of run. So basically, if you take the inverse tangent of 0.02, you'll get the angle for 2%. If you divide, or if you take the inverse tangent of 0.03, then you'll get the degrees for 3% grade. And they both are right around 2 degrees. So that made me feel a little bit more confident that the numbers we used were somewhat reasonable. So again, in this case, it wasn't a very big deal, but to go 30 miles per hour with a 500-meter curve, you only had to bank the curve at about 2.1 degrees. Of course, the opposite is true, that if there really is no friction, and if you bank it too much, or if you bank it even at 2.1 and you go around the curve, say at 20 or 10 miles per hour, then there's a chance that you'd actually slide down the incline. So that's another neat constraint that you got to pay attention to when you're an actual driver. I hope this helps you. Have a good day.